Ready to go?
All right. Thanks everyone for being here. So welcome to today's coaching seminar. It's my pleasure to introduce Taylor Dupuy, and he'll give us an introduction to the Jacobi bound conjecture. Thanks, Taylor.
All right. So thank you very much. So I know this is I think I was planning for a little bit longer of a talk. I just realized it was a 40-minute talk. So I'm going to try and get through the stuff that I can. I'm going to talk about some stuff I'm doing with David Zurich Brown. But I think probably mostly what I'll get to is background. We'll see where we get. All right. So first I need to set up some preliminaries. All right. All right. So I just need some notation. So I'm going to take, so if I take u to be a differential polynomial, like u prime prime plus y, 2z, and then we'll do cubed here. And it's going to be in a ring of differential polynomials in three variables. So the notation that I'm going to use for orders, right? So the order of u with respect to x, this is 2. The order of u with respect to y, right? This is 0. And then the order with respect to z, this is sorry, of u with respect to, sorry, this is u here and u here. U. So this is 3. Okay, so this is some notation that I'll use for orders. Okay, and then one thing that I do want to talk about is dimension. I'm going to be mostly talking about absolute dimension or curl dimension. So let me move that over here. So dimension, and let's start with an example. Okay, so let's consider, um, this derivative here, and this is two derivatives, right? Inside this ring of differential polynomials, this is x prime, x prime prime, right? And we look at its associated differential ideal, right? Which is x prime prime, and then we can do third, and then we go to the fourth, and it keeps going like this, right? Then so this is the differential ideal, right? And what we could do is we can consider the quotient by this. Then we have that here, modulo this differential ideal, looks like so. So this is here, this it kills everything but x and x prime, right? And we see that this thing here has a curl dimension 2, right? Or the fraction field has transcendence degree 2 over the base field, okay? Um, and so one thing that I want to note here is that so if we think of this x as depending on some variable t, so right, if we think of x as depending on t, um, the general solution of this thing, well, it looks like, well, x of t looks like at plus b here, and you'll notice that there are two constants of integration, right? And so the curl dimension of the ring has something to do with the number of constants of integration, and that's essentially what this the Jacobi bound conjecture is going to be about. It's going to be about determining the dimension of a differential variety, right? Um, in terms of the orders of the differential equations. Okay, so just kind of some notation here, right? So just if we're given sigma is a differential variety, differential scheme. I'm going to let sigma infinity. So I'm going to use Boolean's notation. So this is so usually all my things are going to be embedded into some scheme. And so this is going to be the underlying scheme uh, in the ambient jet space, infinite jet space. Okay, just like we were drawing before. Okay, And then this notation here, a sigma, and so this is going to be just the usual dimension, the schematic dimension, or the Kroll dimension of this scheme. Okay, so this is the absolute dimension, not to be confused with the differential dimension, right? And so, whenever there's something going to be finite absolute dimension, the differential dimension is going to be a zero. Okay, so the absolute dimension, not to be confused with the differential dimension. Okay, so there's kind of two pictures that we have of right. So on one hand, we can consider the intersection of two differential varieties, so squared, and gamma could be, say, x prime is equal to 0. All right. You have this kind of differential dimension picture, right? So this is the differential dimension picture, right? And they intersect here, right? Have differential dimension 0 intersection. Okay. And what you can do is you can actually zoom in here and to get a picture in absolute dimension, and you can look at what the components of these things are, and you end up getting, something here that's going to be a positive dimension. You actually, for this decomposition, you actually get two irreducible components, right? One is going to be of absolute dimension 2, and then there's going to be another one that's of dimension 1 that's contained inside of it. Um, and so, kind of the idea is that in differential algebra, right, um, where we usually have finite intersections in usual algebraic geometry, they turn into things that become positive dimensional algebraic varieties, and we read off the dimension of those varieties as sort of the intersection number. Okay, so I'm going to state the Jacobi bound conjecture now.
Taylor, we have a question in the chat.
Yeah.
Is absolute dimension just the value of the Cauchy polynomial of a generic point?
Yeah,
Thank you.
I think that's the typical differential dimension, I think in Colchin's terminology. All right. So let me start with Bezout, right? So Bezout's theorem says if we have F1 through Fn in some, okay, let's say we're working over a algebraically closed field, okay, of degrees d1, d2, up to dn, okay, and the what we'll do is we look at this variety here, x, right, and so this is say the a and k to the n, so these are vectors such that f1 of a is equal to 0 all the way up to fn of a is equal to 0. Okay, so we're supposing that this is a finite set, right? Then, if we have this, we get that the bound on the number of solutions here is less than the product of the degrees. Okay, so this is a classical version. So we suppose some sort of finiteness, and when we have finiteness, we get a bound. Okay, and a classical example is where you take two degree 2 curves. This is d1 is 2 and d2 is equal to 2. And then we see that we're going to get an intersection in 4 points. Right, so this is kind of a classic picture. Right, you could, when you're not proper, right, then you have this inequality, and that's why we have the inequality instead of the equality there. And so in differential algebra, there's a conjecture called the Jacobi bound conjecture, which has a very similar statement. Okay, so here we're going to work with k delta. This is a differential field. well, you can suppose it's differentially closed and where it's going to be characteristic 0. Okay. And what we're going to do is we're going to take differential polynomials now in n differential polynomials in n variables. And we're going to ask the same question about the size of the intersection, right, of the varieties, of the differential varieties. Okay, and so what we're going to do is we're going to let sigma, okay, so this is going to be the phi in k such that u1 of phi, this is 0 all the way up to un of phi is equal to 0. Okay, then we also suppose some finiteness hypothesis. So what we're going to do is we say that if sigma 1 is an irreducible component of sigma of finite absolute dimension, then what we have is that the absolute dimension here, the intersection, kind of the intersection number of these things, so this is going to be less than the Jacobi bound. Okay, so this number here, so this is the Jacobi bound conjecture. This number here is the Jacobi bound, right? And so this number is it's the maximum over all permutations. Oh, excuse me. The maximum over all permutations, where we take the sum from j is equal to 1 up to n of the order of each equation with respect to each variable. So we kind of mix and match an equation with a variable and take the sum of the orders. Another way to view this is that this is like a tropical determinant of the order matrix, if you want. That's another way to remember it, with the max plus. Okay, so this is the Jacobi bound conjecture. Okay, and then there's a long history of work on the Jacobi bound conjecture. So the Jacobi bound conjecture was stated as a theorem in a manuscript of Jacobi in 1865, right? And then in 1935, Ritt realized that Jacobi didn't have a rigorous dimension of order, right? And the way that it was stated was that, well, the number of constants of integration that were needed, right, in order to solve the system of equations, right, was given by this Jacobi number, right? So Ritt used transcendence degrees to give kind of a rigorous formulation of this, and decided that Jacobi's proof wasn't really a rigorous proof. At that time, he gave a thing called the Ritt bound, where if you take the order matrix and you just look at the columns and you take the maximum of each column and then add those up, that's a bound for the dimension on these finite dimensional components. He proved the two-dimensional case and he proved the linear case. After that, there's a bunch of other work. So there was some work of Greenspan, Cohn, Landau. So that for 1959 was Greenspan. Landau did the order 1 case in what's the so-called strong case. Then there's work of Tomasovich, who moved some of that work to PDEs. In 1982, there was work related to characteristic sets, and I might get to that, of Kondratьeva, Mikhailov, and Pankratiev. They also have a 2009 paper. And also Lee and Lee have some other work on characteristic sets. And Olivier had some work in 2007 with Sadek, and then there's another paper in 2022 which goes over kind of some of Jacobi's old stuff, which I think is really nice too. And I guess the other last thing I should mention is Hrshovsky in 2007 has a 2007 preprint on the archive, which claims the difference case in full generality. Okay, so the first open case, let me just write this down. Okay, is the case of quadratic order 2 in 3 variables. Okay, so 3 variables, 3 equations, and so this would be the kind of the first case that's completely open. Okay, and so what I want to do now is go over some stuff that Olivier and Sadek have done, and give kind of a geometric interpretation of what they're you know of linearization and how to relate this to linear differential equations, which is something that RIT did. And then I want to show how we can prove the Jacobi bound conjecture under hypotheses of when your system of equation your system has nice linearization, meaning that it's reduced. And then time permitting, or if you guys ask questions, I have prepared some examples which show some of the ugly aspects of these, so kind of some bad linearizations, and how some of these techniques won't work in these cases. Okay, and kind of all the bad things that can happen. Okay, so the first thing that I want to do is I want to talk about first order perturbations. Okay, so this is something we all learn in the an ordinary differential equations class. So this is a method. This is a method of linearizing ODEs at a known solution, right? And so what we'll do is we're going to take sigma, and then we're going to get some linearized equations at eta, a known solution. Okay, and so the basic idea is like this. Okay, so what we'll do is we take kind of a nonlinear differential equation, okay, and then we expand using that x looks like x0 plus epsilon x1, where epsilon squared is equal to 0, and x0 is a solution. Okay, so what we do is we just plug this in, right? And so maybe I'll do this. Well, I guess I can do it here. X0 plus epsilon x1. We take the derivative of this, and then we cube it. Cubed plus. All right. And so what I'm going to do here is I'm going to expand this out, right? And I'll do this on the next page. All right. So we have x0 plus epsilon x1. The derivatives distribute. And then here we had a cubed. So we have x0 cubed plus 3 x0 squared x1. And then we have an epsilon here. And then we had we had an x0 plus epsilon x1, I think. And so what you end up getting here when you work it out is x0 cubed minus x0, okay, plus epsilon times x1 minus 3 x0 squared x1 minus x1, like this, 0. This thing vanishes because x0 is the solution, right? And then this thing here is now a linear differential equation, linear ODE, okay? And so this is the linearization, right? This is the linearization that you get. X0 now is there. And so the kind of the geometry of the situation here, you can do this generally, right? Is that we're going to have another differential algebraic variety over a given variety. And if we're given a solution here, we can look at the fiber here, and this is going to be the linearized variety at phi, at some solution phi. Okay. In terms of you know, uh, uh, functorality or like the interpretation in terms of functor points is that if you have a differential algebraic variety, or if you have a differential ring and you look at the A points of it, it's the same thing as looking at the A adjoint epsilon mod epsilon squared points of your original variety. Okay. All right. And then there's a general formula, right? So if we're given U, which is in here, let's say it's up to order R. Okay, then then we can write down a formula here for this thing. So U of eta plus epsilon y. So y is now a vector, eta is now a vector, and so we get that it's U of eta plus epsilon times some some kind of a gradient here, uh, evaluated at eta, dotted with this thing here. Okay, and so this thing goes away, right? And you just get that this is du d delta r x evaluated at eta dotted with this new variable y. Okay, where this thing here, I'm using Boolean's notation. This is like y1, y2, yn, so y1 prime, y2 prime, yn prime, and then it keeps going, and then you take the rth derivatives, ynr. Okay, and then this partial derivative thing of x here. So this thing here is, well, you just take the partial derivatives with respect to all the things. Du y1, du y2, all the way up to du yn. All right, and then it continues, and then you do all the derivatives here. Y2r, oh, sorry, these are x's. So I just did it with y, I guess, but all right. Du dynr like this. Okay, and so then the linearization of u at eta, well, it's just this formula that I just wrote down. R x, and then we evaluate it at eta, and we take this dot product here. Okay, so this is the formula for the linearization. Okay, one thing that I want to first say, the thing that I want to say now is, okay, so we can have these differential equations and then we can linearize them and we get a new system of linear differential equations, okay? So the lemma that I want to say is, so lemma, so I want to tell you that linearization respects the Jacobi number. Oh, the Jacobi bound, sorry, there's like some stuff right there. All right, so let me explain what I mean by this. So what I want to say is that okay, so let U be in here. Okay, so if I take some U in here, right, and what we'll do is and we take eta, a solution, or actually we just need eta to be in K, K to the n, right? Then uh, actually we do need to be a solution. Right. So what I want to say is that the order of xi of u, this is greater than or equal to the order, this thing of xi of L u eta. Okay. So this is the first thing. And so if, okay, and so this thing implies that the Jacobi bound to the linearization, right? And generally, that if you have that, if you linearize the system, L of U1 eta, L of UN eta. So this is less than or equal to the Jacobi bound of U1 up to UN. Okay, and then we get equality, right? When separates don't vanish. Well, I'm going to say, I'm going to put this in quotes, separates don't vanish. Okay, so meaning that you need certain partial derivatives to work. Okay, so let me just kind of explain this real quick, right? So the order with respect to xj of this thing here of u, so this is max plus. Okay, so when I do a max plus like this, I mean that it's going to be the maximum of the stuff in the set or zero, c greater than or equal to zero, such that du dxj of r, this is not zero, right? So that's what the order is, okay? And if you just look at the order of the linearization with respect to the variable that we're linearizing at, L, do this, LU of eta, like this. So this thing here is max plus of, okay, so we look at the set of R in z greater than or equal to zero, such that we do the same thing. So we do this du d xj of r, but now we evaluate it at eta not equal to zero. Right? So what may happen is that some of these partial derivatives here may vanish, right? And when those partial derivatives vanish, this order goes down, right? So you may have fewer non-zero derivatives, which can make the order go down, right? And so that's kind of that's the idea. It's very simple. Okay, so when you linearize, the Jacobi number can go up, or sorry, go down. It can only go down. All right, all right. All right, and so then you since it's only since the Jacobi number is essentially a function of the order matrix, and the order matrix can only go down, right? Well, that means the Jacobi number has to go down as well. Okay, so linearizing does respect the Jacobi number. Okay, so all right, so now I want to talk about another version of linearization, and that's via the tangent bundle. Okay. And so recall that for a scheme X, right, what we can do is we can look at the tangent bundle of the scheme. And so this is global spec, right? So this is global spec. Let's say over a field, right, of the symmetric algebra of omega of x over k. So this thing here is the symmetric algebra of the cotangent sheaf. So this thing here, so this is the big direct sum from j bigger than or equal to zero of these symmetric algebras here, j of omega x over k. Okay, and so this is the tangent bundle, right? This is one of the definitions of the tangent bundle. One way to remember this is that the functions, right? So if you can remember that differentials eat they eat tangent vectors, right? And you want functions on your tangent bundle, right, to eat tangent vectors. And so that's one way you can remember if you can ever remember whether this is it or its dual. Okay. And so what I want to say now is that this description of the tangent bundle is the same thing as the first order perturbations. Okay. But first, I want to tell you a lemma, right? The lemma that I want to tell you is that so if X is a G variety or G scheme, let's say D scheme. So it's has a derivation on it, then so is T of X, this tangent bundle. Okay, and so let me do this. So the whole point is that the tangent bundle under its natural definition is when you take it for a differential scheme, it'll still be a differential scheme. Okay, so all right, and so let me do this by an example, right? Okay, so if we look at J infinity of A1, right? So this is spec of K of X, right? It has all its derivations on it. It's just the differential polynomials in one variable, right? So this thing here is K of X, X prime, X prime prime, and so on, right? We can look at omega of this thing over K. And what this looks like is, well, it's a big direct sum of two things from I is equal to 1 up to n, and j is equal to j is bigger than or equal to 0 of, well, you have your original ring here, and then you take d of all the indeterminates. And all the determinants look like this, right? So they look like the various, oh, sorry, we're only doing one variable. So this is, excuse me. So we're only doing one variable, so I guess I just don't need this part. And I can cut. Let me move this over. Let me just write it. Let me write it. Okay, K, X. We have dx j, like this. Okay. And so, okay, so then we have this thing, and when we take the symmetric algebra, right, we essentially are looking at an algebra where we're allowed so this is a free module, and we're essentially looking at an algebra where we're allowed to multiply generators, right? So the symmetric algebra of this thing over K. So this thing is just, well, it's K of X, and then we have dx, dx prime, dx prime prime, and so on, right? So it's an infinite dimensional thing, okay? And this thing actually has a delta structure on it, so it has a derivative structure on it, and it's not just the d, right? What we do is we define d of these things, dxj. Well, we define this to be d of, well, xj plus 1, right? And so what this does is this makes this a differential ring, right? And so the tangent bundle of the infinite jet space is naturally a differential ring. And so the kind of the upshot here is that this thing here, T of the upshot, is that T of J infinity of A1, right, is a T scheme, right? When you take it. So this is what we showed. Okay. So, all right, and then this kind of works out in general, right? So the theorem is that, okay, so here's what I want to say is that we kind of have two ways of making new differential varieties out of old differential varieties. The first one was doing, okay, we linearize the equations, and then if we linearize the equations and take the kind of the differential ideals generated by those linear differential equations. The second thing we did was we do this weird, the global spec of the symmetric algebra of the Kähler differentials, and those two things agree. Okay, so the theorem that I want to say is that, right? So linearizing, so the, the two perspectives on tangent bundles agree, right? Is that if you take this thing and then you look at its infinite jet ring, so this is going to be equal to or isomorphic to the tangent space of the thing inside the infinite jet ring. Okay, so so that uh, the yeah, so that's what I wanted to say about this. Okay, and then you can prove it directly. So the linearization, okay, so the proof is kind of easy, but the point is that the linearization for linearization is just taking D, the exterior D of equations. Okay, so that's the point. Yep. Okay, okay. So um, now from here, what I want to do is I want to talk about how we can prove the Jacobi bound conjecture, right, using the linear case and using linearizations for systems with nice linearizations. Okay, and uh, okay, so let me kind of let me do this. And to do this, we what I want to do is I want to talk about generic smoothness. Okay. Okay. So what we want is so we want to use so what we want to use that um, that reduced varieties, so usual varieties are reduced irreducible are generically smooth. Okay. And what this allows us to do is this tells us is that we can read off the dimension of a variety from its tangent space. Its tangent bundle, or I can say tangent space at a generic point. Okay, but our issue here that we have to face is one of the issues that we face is that our theorems apply to things which are so these theorems apply to finite type rings. Okay, but our rings are not like that, right? Our rings look like this. So they look like K, X1, Xn, mod, right? This graph here, right? This is infinitely generated, and this is infinitely generated, right? So like we don't get to use generic smoothness for these differential varieties, these schemes that we're cooking up, where we're taking an infinite number of indeterminates and we're modding up by ideals. Okay, all right. So, um, all right, and so how? I'm almost out of time, huh? How much?
Yeah, it can go 5 minutes or so.
Okay, okay, okay. So, so what I want to say is, okay, there's a lemma that you can prove. Let me just kind of tell you the lemma, right? Um, all right. So is if sigma is integral, meaning it's reduced and irreducible, and its absolute dimension is finite, right? Then there exists some u in here, which is dense and open of finite type. Okay. Okay. And then what you can do from this is you can prove a sort of generic smoothness for differential algebraic varieties. So a corollary of this. So this proof uses differential fields and essentially uses that you know that you how to present differential fields. And then you get this generic smoothness for differential varieties. Okay. So it says that if sigma is reduced and sigma 1 is an irreducible component with generic point A to 1, then the absolute dimension here, well, this will be the absolute dimension of the tangent bundle at the generic point, right? So, and the key hypothesis here is reduced, okay? And you can walk through this step by step, okay? But once you have this, right, so then you can prove the Jacobi bound conjecture in the case of reduced varieties, right? So so then so the JBC for nice linearizations. Uh, no, uh, sigma. Okay, and so the theorem, this is our theorem, right? Says that if sigma looks like this, with these guys here, and we have the hypothesis that sigma here, this jet scheme here, or the underlying scheme here, is reduced, i.e., that the differential ideal here is the same thing as the radical, which, let me say, be honest, it doesn't happen a lot. Then, I mean, it happens sometimes, right? Then, for every sigma 1 that's irreducible here, if this is an irreducible component of finite absolute dimension, we have that this thing here is going to be bounded by the Jacobi number here. And like, yeah. So so this is something we can show, right? And the key hypothesis is this thing about the linearization behaving well. Okay, so I am going to stop here, and then if you guys have questions, I can tell you more about like how badly things behave when you try to like. I can give you an example of where this doesn't work, and kind of what happens after this.
All right, thank you. Let's thank Taylor for his great talk. Thanks, Taylor. Do we have any questions for Taylor?
Oh, hey, Jim's the one who, yeah.
So yeah, so if we don't have any question, I'll be happy to see the example where that doesn't go and why. If it's
Yeah. So, okay, let me show you. So at the generic, okay, so let me show you an example, right? So here's some ugly. Jim, did you have something you wanted to say? So, by the way, Jim pointed out some of these ugly aspects.
oh
So, so thank you, Jim. All right. All right. So here's an example, right? And if you just kind of look at, so this one is its own linearization. Okay. But if you look at this one, right? So if you look at like x0, oh, so we'll write x epsilon x1, y is equal to y. I said that this was joint work with David Zurich Brown, right? It is, if I didn't say that. Okay. So if we look at this thing here, this first one here, you see this square, right? The square, as people know, it's gonna separates are gonna get messed up once you start having squares involved, and that's essentially what's going on in this thing. But let's look at the linearization of U1, right? Okay, so what we do is we do this at x prime, but we evaluated at x0, y0, x1 prime, du1, dy, x0, y0 at y1. Okay, and this becomes 2x0 prime, y0, x1 prime plus 2x0 prime plus y0, y1. Okay, and the point is that so this x0, y0 needs to be a generic point to be generic for the radical, right? Okay, something that's in the radical of this thing. So here, if we take this one, we have x prime plus y squared, y prime plus x, like this. So once we have a square in there, right? Well, this thing has, I think it's this whole thing, but if you do x prime plus y, y prime plus x, okay? And so this in particular implies that that x0 prime plus y0 needs to be 0, right? And so once you have this crap happening here, right? What you'll see here is that this has to go away. And so what happens is that this thing has a good linearization, but this one doesn't, right? And so there's a whole linear equation that vanishes, right? And that makes it so that the tangent space, right, becomes as positive differential dimension. So you don't get a read at all, right? You don't get you know, it just doesn't work anymore because you're no longer in the hypotheses of the Jacobi bound conjecture in the linear case on the tangent space. Okay. That being said, right, if you have a square, you can just take, that there's another system of equations, right, where you get to take the roots of all that stuff and it still holds. The Jacobi bound conjecture holds for this one. But the thing is that there could be much more complicated things that happen, right, than just taking powers. But if it's just powers, you're fine. Let me also say, right, okay, so maybe someone will ask about characteristics, so I'm going to pause again and I'll say more if people.
So we have one question in the chat by Williams Seth, and he's asking, do you know any criteria or cases where the Jacobi bound is reached?
Yeah, I mean, so if these parts, okay, for example, if they're it's reached, yeah, okay. So for example, characteristic sets. So if you have a set of equations which define a characteristic set, then uh, for this particular component, okay. So so you have a prime ideal, right? It has a characteristic set, and the saturation of the thing generated by the elements of the characteristic set with respect to its initials and separates, that's going to give you the prime ideal. That by definition tells you, right, that the separates are not going to vanish, right? So when you linearize at the prime ideal, and actually, right, the Jacobi bound in this case is equal, right? The Jacobi bound for this particular thing is equal to the dimension of the variety, right? So it's not just that they're you get a bound; it's that it's equal on the nose.
Thank you.
Thank you. And Jim also has a question. Is there a sense in which the Jacobi bound for difference and differential equations are related?
Yes. Okay. So there is like a deformation theory that you can do. This is something that we're looking at where it turns out that if you use Booleans, so he has this paper that's about I don't know what he calls it, like arithmetic analogs of derivatives. Okay. So if you look at that and you look at what he does over a field of characteristic 0, he kind of classifies operations, right? Where he classifies operations, right, which satisfy some rule and a product rule. In this, he actually ends up writing down I don't want you to say something scary, but he writes down a stack, right, which is essentially A1 mod GM. And what it does is it shows that you can take kind of a general operation, right? And as you go to the kind of the closed point of the stack, you get derivatives. And if you're on the open part of this thing, kind of the Orby part of this stack, you end up getting the difference operators. And so you can specialize kind of like abstract differential equations in the sense of, you have a general operator which can specialize to difference in differential equations. And it turns out that the closed point of this thing gives you the differential equations. Okay, and so you can use this to relate the difference in differential cases, but you can't use, but it goes kind of the wrong way, and you can't use the difference case to prove the differential case. You can get stuff going the other way, from the differential case to the difference case, using the semi-continuity stuff, right? And I don't want to say anything definitive on that because we need to write it all out, but it seems to be what's going on is that you can go from the differential case to the difference case, but not the other way. Although I guess you can say generic, there are things about things holding on opens that you can say.
All right. Thank you. Do we have any other questions for Taylor?
Yeah.
Is Alexi here? Oh, sorry. Why did you go, Will?
Hi. I'd like to ask, what are the consequences or corollaries if the Jacobi bound is proved in general, say to computing things?
So I don't really, to be honest, I don't really know, but I do know that. Okay, so this is a good question. So like, I think it might. I don't know do anything about control theory, but I think some people, there may be stuff in control theory that people do. I don't know about that. One thing I can say is like, okay, I told you that it holds in these characteristic sets, and one thing that you might hope to do is to take this Rosenfeld-Grosvenor algorithm, right, and kind of go step by step and see that the Jacobi number goes, only goes down, right? And so if you can prove good bounds on good things happen with the Jacobi number as you step through the Rosenfeld-Grosvenor algorithm for producing the characteristic sets, then you could hope that you would arrive at you'd be able to prove the Jacobi bound conjecture, right? But it turns out that you can't do that, right? Because there are examples. So we found some examples. I can write down, let me write down an example. Okay, so if you write down this particular example, U1 is x to the 100 plus y prime plus c prime.
Taylor,
U2,
sorry to interrupt. Do you expect us to see something at the moment, or?
Oh, I do expect you to see something, but
Which
it's
we
not
are.
showing up.
Yeah.
Let me stop and start. All right, share. Okay, there it goes.
Yeah.
Okay, so I was writing. Okay, so all right, let me write this equation down. So where is it? Oh, here it is. So x to the 50 plus y plus z, u3 is equal to x prime plus y prime plus 1. So Alexei has a bunch of papers, and I think a bunch of other people have papers where they were looking at order bounds in these characteristic set algorithms, right? And I was wondering if this is what they were after, if they were interested in the Jacobi bound conjecture explicitly when they did this, which goes back to kind of William's question. I don't think they stated explicitly. Okay, but if you step through the Rosenfeld-Grosvenor algorithm here, so the original J is 101. And then as you continue, right, what ends up happening is that J goes up, right? And so, you know, if for this particular example here, you know, you go and you're going to go try and generate a characteristic set, right? And as you step through, right, at least in the implementation that we had, right, it goes from 1 to 1 and then it goes up, right? So like if you look at trying to eliminate here, you have to take 50 derivatives of u2 and apply it to u1. And when you take 50 derivatives here, what ends up happening is it changes this first equation, right? And then the Jacobi bound will end up going up. So there's, it's, you know, even in this linear case, it seems pretty bad to kind of look at stepping through.
Okay. I have another question.
Thank you. So, William, if you don't mind, before you do that, unfortunately, I have to rush to campus. So I'm going to stop the recording and leave the session open so that you can still talk. And thanks, Taylor, for the great talk.
Sure. Thanks.
So you